Hi, I'm Randall Heyman, a mathematics academic. You're on one of my Corona Help playlists where I make quick turnaround videos to help students and educators. If you'd like me to help you, then drop me an email or comment below any of my videos, and if I think I can help, I'll make you a video. Okay, so I got a comment under one of my videos from someone, Harshit, I think it was, yeah. And he asked about the Mobius function and Mobius inverse. So I'm just going to put a few thoughts up, and he or anyone else can come back to me if they've got further questions. It's a pretty deep subject, so I can only give you a bit of an overview. So regard this as an overview. So the Mobius function, a bit notable, it's got the double dots over the O every time I do a paper. And most of them have got Mobius function. I always seem to have to work out how to put the double dots there. Okay, so the Mobius function is an arithmetic function. Sorry, let's do this better. Let's first talk about the Mobius function, and then we'll talk about Mobius inverse after that. Okay, so this Mobius function is an arithmetic function. Arithmetic functions are functions, so here you should be thinking sort of some function f, which goes from the complex numbers to the naturals. In what we're going to be talking about, this will be a natural as well. So, but the important thing is that the output is a natural number. So, examples of arithmetic functions are the divisor function, the number of divisors of n, pi n, the number of primes less than or equal to n, etc. So the Mobius function, uses the mu, so I suppose we could say it's denoted by mu. Okay, so how do we work it out? Well, it seems a bit confusing at first, but it's actually, it's not too bad. I mean, the reason why we bother with all of this is actually a very important function. So it equals 0 if n has a square divisor or factor. I'll do an example in a second, square divisor. And it equals -1 to the power of r. So that means just something that is either -1 or 1. And here, so if n is not if n does not have, that's a square divisor. If n doesn't have a square divisor, does not have a square divisor, it must be of the form p1 times p2 ... pr, where these are all different primes. Okay, so let's do some examples. U8, well, 2 squared, so that's divides 8. So 8 has a square divisor, so therefore mu of 8 is equal 0. What about the Mobius function evaluated at 6? Well, 6 equals 2 times 3, so therefore r equals 2. There are 2 primes, so mu of 6, the Mobius function, is equal to -1 to the 2, which is equal to 1. We also say that mu1, well, for mu1, well, it doesn't have a square divisor. And actually what we do is we say, so it's down here, but we say that r equals 0, and therefore mu of 1 equals -1 to the 0, which is equal to 1. And I mean, just to give you a -1, I suppose mu, what about mu of 2 by 3 by 5. What's that? Well, actually just the primes. So mu of 3. Well, 3 equals just 3, r equals 1, and therefore the Mobius function evaluated at 3 equals -1 to the 1 equals -1. Okay, so that's how that works. I can only give you a bit of a smattering about why it's important. It's got a link to the Riemann zeta function. If you're interested in the Riemann zeta function, I've got an intro to the Riemann zeta function video, which is quite nice, graphical understanding of it. Okay, so the Riemann zeta function is this, zeta s, and it turns out that it equals the sum from n equals 1 to infinity of the Mobius function inverted. So that's the link there. Another just interesting equation is that the sum of the sum of all these mu n's for all the divisors that divide n is equal to 0, except if we just use 1, we let n equal 1, well, that equals 1. So that's an important one. It also helps with going from sum to a product. So if f is an arithmetic function, but in particular if it's multiplicative, what does that mean? i.e. f of mn is equal to fm times fn if the GCD of m and n are equal to 1. So if m and n are co-prime, then this must apply. So a lot of functions are multiplicative. And if that's the case, then we have this really beautiful thing. So here we have a sum. And what we find is that that is equal to the product of p prime. P divides n of 1 minus p. That's not quite right, is it? I think it should be function of prime. Let me just stop there. I'll just check that I get that right. I'm pretty sure it's fp. Yeah. Okay. Yeah. That's I had that wrong. I thought that was wrong. This should be the function of the primes. If you're interested in any of these, particularly that I go through, I'm happy to do some examples. Okay, let's move on now to Mobius inversion. And this allows us to essentially reverse something that we're interested in. For example, often we'll be interested in this sort of idea. We've got some function, little f, and we're interested in summing it for all the divisors up to n. I mean, you've seen that already in what we've done just above. We've had quite a few here. We've had a d divides n. Here we've had a d divides n sum. So already we can see that that's not uncommon. And what the Mobius tells us, Mobius inversion tells us, is that we can express it another way. So it enables us to invert this. In other words, it enables us to express fm as something. And it turns out that it's d divided by n of this f, this big F, the sum f, times mu of n over d. So here, this is where we've got Mobius. That's why it's called Mobius inversion. And this is very valuable because it enables you to just willy-nilly go, well, just to go back and forwards between this expression for f, big F, and little f. Okay, so Harshit, I hope that's helped you with a bit of an overview of Mobius function and Mobius inversion. If you've got any specific questions or you want some examples on anything I've done here or some other ideas in terms of either of these things, then let me know. But more generally, if anybody's got any questions about any aspect of mathematics during the coronavirus, contact me, and if I think I can help you, I'll upload a video or videos if necessary.